Hello everyone and welcome to this tutorial on loops. For loops in particular, we would be discussing what a loop is, as well as how and why we may move away from this wonderful programming construct called loops. So today we would be discussing two examples. Both of them you have seen in some form in this course as well as earlier. Question 1 would be discussing dot products, and question 2 would be discussing tier ratings and doing some operation with tier ratings, which you have already seen in lab 1. So now we can begin. So question 1 says, given vector y and 4 other vectors x1, x2, x3, x4, which one goes most in the direction of y? And this is actually the definition of dot product. The dot product actually tells you the amount of one vector that goes in direction of another. So as we have seen in class, the dot product can actually be defined as the sum of element-wise product of the vectors, as well as some of you pointed out that the dot product can also be represented as magnitude of vector 1. Say we have two vectors x and y, so it would be the magnitude of x multiplied by magnitude of y multiplied by cosine theta, where theta is the angle between the two vectors. So where do we bring in loops here? So the thing is that we want to compare y with all these four vectors. And this is actually an ideal scenario where we may bring in loops. So what is a loop? A loop is a programming construct that helps reduce redundancy by actually incorporating repetitive or actually representing repetitive tasks in a manner that can be executed repeatedly, eventually giving an answer. And what I mean by it would soon be clear. So I think to avoid distraction, I can just switch off my video. All right. So first of all, we can begin with visualizing what these vectors are and see what dot product means, as well as we will briefly discuss or elaborate on the intuition of dot product being somewhat similar to correlation that we pointed out earlier in the lab lecture 5. So for visualization, what you have seen already is using plot command, but I would be using a quiver command that actually um, helps us visualize vectors by a vector-like output. So first of all, I'll just show you how this works. So if first of all, I should run this, run in advance. All right, actually everything runs by itself. So quiver actually gives this vector-like arrow, as well as so the first two elements are actually the coordinates of point A. So 0, 0 is the origin, and 1, 1 is actually present here, and it helps us visualize vectors. So now what we want to do is we want to visualize all these vectors to help us see how they look. So based on this construct, I actually can begin with defining the origin. So it is 0, 0. I can place a comma, I cannot place a comma. Then I use this quiver command. There's origin 1. So this is where my vector begins. And then I'll have, like, let me just visualize x1. This 0 that I put towards the end is just to help with some scaling issues. So now I run this. And I see this 0.5 and 5. So this is a vector visualization in the 2D plane. And I have actually plotted x1. And let me plot everything together. So I can just begin with y, origin, So if I do this, what will happen is that both of these would be plotted separately. So both of them are being plotted correctly, but I want them to be plotted on the same plot. So we have seen this hold on command for it, and I'll just immediately afterwards put hold off. Now what I would be doing is I would be actually plotting all these x2, x3, x4 as well on the same plot. I'm actually copy pasting it because I know that I have to repeat the same thing again and again. This would be x2, x3, x4. All right, so these are being plotted correctly. So we have x1 0.5, 5. So this is this red vector, and then we have 2 3, which is this yellow vector, and so on. For an ideal plot, I should have actually provided this with the title as well as legends, but since it isn't as straightforward as plot here, I'll just ignore it, and this is also not the main point of discussion here. So, but what I notice here is that I was doing a lot of copy pasting. If I had to compare y with actually 100 vectors, it would have been too much copy pasting or actually writing the same lines of code again and again. And this is actually an ideal scenario where I can actually use loops to actually remove this redundancy, since what I am really doing is I am just using x1 here, x2 here, and all these are vectors of same dimensions. So now I'll show you how I may use loops here. So I'll do visualization using for loops. All right, so I can just reduce the command window a bit. All right, so first of all, I want to, since I would be looping over these x's, so let me make one x which contains all these individually, x3, x4. I don't put a semicolon here so that I can actually help you see what my matrix x contains. Yes, so here's my x actually. So I have 4 points, x1 to x4, which correspond to the rows here, and the first column actually corresponds to the x dimension and y dimension of first dimension and second dimension. So it's like x1 is 0.55 and it is actually 0.55. All right, so now I would be using loops. So what I want to do is I want to actually loop over this x and first plot this 0.55, which is the first row, then the second row, and so on. So since I would be using hold on, let me just plot y originally, and then I can loop over x. So what I would be looping over is actually I want to repeat this quiver command actually 4 times. And what does this 4 correspond to? It actually corresponds to the dimension of the number of rows in x, because this is how I have prepared x. So what I would be doing is size x would actually be returning me 4 cross 2, but I want the number of rows. So this, and when we start a for loop, we have to end it. This is like the MATLAB, how MATLAB actually, the syntax for defining a for loop in MATLAB. And now what I would be doing is I would be using the quiver command and origin 1. So my origin always remains the same. But what actually changes is that now I want to plot the first row and its first index, and or actually ith row and first index, ith row second index, and I'll just put this 0 here. But even if I don't, it won't actually matter a lot. And eventually I need to do hold off. All right, so let me run this. Yes, so this was the original plot. Now this is the other plot using loops, but this is an easy construct. Even if I have 1,000 x's to plot, the total lines of code would be the same. There would be x4, x5 till x100 here, but otherwise this code would remain same. Whereas if you would have gotten rid of for loop, I would have actually had to repeat similar lines, changing just this 4 to 5 and up, down till 100. So this would be 100 lines of code versus just a couple lines of code. So now we have performed the visualization. I also want to repeat the concept of dot product. So as we saw here, dot product is the amount that one vector goes in direction of other. So what that is, my reference vector is here, y, and I want to see how much this x1 goes in direction of y. So this is just the perpendicular projection or orthogonal projection onto it. This is not like exact, but so I've taken a simplistic example of y actually being the unit vector in the direction of x-axis. So this would be very simple. So the dot product would give us this vector actually, and for this yellow vector it would be this vector, because when we project this orthogonally, or we will see that, all right, how much of this yellow vector actually goes in direction of that original blue vector, we get this result. And through this visualization, we already know the answer, that the vector x4, I think, let me like erase this shit. Yes. So 1 second. Yeah, so I already know that this vector, which has coordinates 3, -1. So, and this is actually x4. So my answer for the maximum dot product would be for x4, uh, which would have a value of 3 actually. Now let's see if we obtain identical results for after performing and finding dot product using for loops, as well as using some functions. Let me clear the drawings. All right.